Hi guys, can I get a sound check?
Yeah, we can hear you.
Great, thanks. Is the audio quality okay? I'm using a different microphone.
Yeah, it's fine.
Okay, great, thanks. Logging in still, just 1 second, guys. Sorry, I'm. Slide text 6, I think. Marie? Yeah. Interesting. So guys, I'm gonna keep, so thanks for your patience, by the way. Sorry, I'm just sometimes I'm bad with my scheduling here, so sorry about that. But anyway, today I'm gonna keep like beating on this concept of gain, and the reason is, I've been in the, if you include grad school, I've been in the circuit design, doing circuit design sort of semi-professionally or professionally for like, I don't know, like 30 years or something. So I'm doing, semiconductor microelectronic design. So, you could say this is my life's work and so on. But, I was like so confused when I was taking this class like you guys were. And, I was basically like confused probably until I graduated with my undergrad degree. Like basically I didn't understand some key concepts. Even the whole first 4 years, I was like, taking these classes, and overall, like these things were just seemed like I was just kind of like the transistor this and gain that, and didn't make any sense. So I keep trying to like try different approaches to have it make sense to you guys in some way, or at least you guys can kind of see what, from a high level view, what where this is all going and how it might be useful. So what I thought is I was gonna like do a little bit of a tangent. So, this isn't gonna be in your test at the moment. I mean, I'm like the first 10-15 minutes. I was gonna introduce you guys to some high level concepts. I don't know if you've seen it before or not, but sort of an idea about where all this is going in terms of actual useful things that you're learning and you'll be using at work or research or whatever direction you'll go in terms of microelectronics. Okay, so a big part of design, any kind of design, is to have reproducible results. What do I mean by that? So if you're doing design as an engineer, okay, so let's say for the sake of discussion that you're an engineer of some kind. In this case, we're electrical engineers studying microelectronics, but whether you're like a mechanical engineer, whatever it is, there's a difference between us in a typical sense and, say physicists. So scientists, they may make instruments, they make, they do stuff, but, either they're studying stuff, or if they make something, they're making a few of it, right? In JPL, I worked at NAS JPL. They're making, typically you're making one camera, 10 cameras, something like that. And so, and then you're taking those cameras, you're putting them, each one of those is, by the time it gets done, they're worth, hundreds of $1,000 or cost hundreds of $1,000, better way to say. Because they go through a lot of testing individually, and they're put into a pretty controlled environment. So the difference with that, with the typical thing you do in engineering, is we want to produce stuff, we want to design stuff that can be produced. Okay, so you want to make design for production. What does that mean? Well, you need something that, imagine if you're making, a microphone, right? And you're making 100,000 of them. If every one of those microphones needs to get tested, hand tweaked, somebody needs to power it up, check that, when your customer is buying a microphone with, a 1 through 10 dial on the volume, they want, when they go to the dial 9 or 8 or whatever it is they're doing, they want a repeatable experience. If they buy 2 of these, when you go to that dial 9, it should be essentially the same. And you sure don't want it to change from time you power this thing on to the other time you power this thing on. That's, I'm using microphone as an example. That's like a handy example for this class. We're all familiar with it, but really anything. Every time you buy 2 computer displays, you want, when you're setting them to a certain brightness level, you want that to be repeatable. You want that to be repeatable from product to product. And if each one of them, each time you are shipping one of these things, you need to have a technician or a production person sitting there tuning stuff, spending hours making sure it's all right before you plug it into, before you ship it, it's not going to be a cheap product or cheap enough for it to be affordable by, like people like us. And that's very likely going to lead to a product that when you have it at home, if things get a little too warm or too cold, or, you go to different homes or different areas, like things are going to look different. So you want something that's reproducible by design. Okay, so that is a key thing. Okay, and so that's a very generic statement about engineering and what things makes engineering different in the industry, or as professional engineers compared to what you do in a research environment, whether that's in academia or a research lab, where you're just kind of like building a onesie twosie thing, right? If you're building something in Cal Poly for a lab, it's unpleasant, but you could sit there and screw around with it for a whole day, tweak it, and hope to God nothing changes. Like tomorrow you come in, you turn everything on, hopefully nobody's moved anything, and you get the same result. You can afford to kind of do that. I mean, it's 8 hours or 10 hours of your time or whatever. You wouldn't want to do it, but you could do it. You could not do these things in an industrial, in a commercial environment, okay, or aerospace, whatever, if you're producing a bunch of these. Okay, so that's at a very high level. Now, let's take that down to a very specific example that you will see a lot. You will hear this word. You will touch this thing, I guarantee you, in your electrical engineering life, and it's called an operational amplifier. Okay, so now why am I bringing up, again, this is not going to be in the test, this is for your background, and so why am I bringing up this operational amplifier? It's because a lot of the circuits we're talking about are individual bits and components in this thing called an operational amplifier. The symbol for it is this thing. Okay. Okay, so that's sort of a generic symbol for operational amplifier. And what it does is, and it seems like, again, like I never understood what this thing does, and I don't know if once I realized what it does, it didn't make any sense to me. What it does is it's a circuit, or you can think of it as a block, as something you buy. It's actually an individual thing you can buy, or it's included in chips, etc. But you'll probably in Cal Poly or in a lot of different places, you'll see that it has individual components that you'd buy and use in your designs. What it does is it takes the difference between its inputs. So it takes this plus input, subtracts the minus input from it. So it just calculates that difference, amplifies it by a gigantic factor, and puts it on the output. So basically the function on the output voltage is, so I'm going to call this V at minus input, V at plus input. So it's V at the plus input minus the V at the minus input, times the gain, times A, which is A is the gain. And for, typical op amps, this gain is going to be, I don't know, a million. Maybe it's 10 million. I don't know. Or 500,000. Very high gain. Okay. So it takes that difference, amplifies to the output. Okay. So, well, again, a lot of the stuff we're designing now is kind of going into this building different versions of the circuit, or understanding this version of the circuit. Why would you, seems like a pretty, like a limiting thing, like a pretty limited, I don't, why would you want to have this minus plus and this V out? Why do you want to do that? Well, it's because, when you have this circuit, you can use it you can use it. Thankfully, our predecessors have come up with lots and lots of circuit configurations where you can add stuff to this op amp and get very precise, very producible different kinds of functions. Lots and lots. If you look at different circuit designs around op amps, I don't know, you'll just books and books and been written, and like if you go to companies that sell these, there's lots and lots of examples of different type of things around this. Okay, so let me give you guys an example. Okay, so let's say in that same microphone, it's not unusual where you have a microphone and you have a dial. You want to change the gain of that microphone. You want to make the output louder, right? So let's say you want to have a gain from that microphone. Excuse me, guys, sorry. I don't know if that really helped, but let's say you have, let's say that didn't help. Sorry, guys. I think I better go draw the drapes, or else we'll keep getting interrupted. Just give me 1 second. All right, guys, sorry about that. So anyhow, so let's say I want to have a microphone with something that repeatably I can amplify the output of that microphone. Repeatedly, I want to amplify it by a factor of 2, 3, 4, 4.5, 4.6, whatever it is, up, let's say to 10. Okay, so let's say I want to have a repeatable producible gain of 10x. Okay, anybody want to take a crack at how I would go about doing that, or any suggestions with what you know so far? No, nobody's no takers. Okay, so we know, or at least I made this claim early on in the class, that if you just have resistors and capacitors, you don't have any transistors, I claimed you can't get any gain, right? You can get like a attenuation of 10x pretty repeatedly, right? You put a R, let's see, you put a R over 10 here and an R, and well, it's R over 9, I guess. Maybe I'm doing this wrong, but you're doing, like basically you can get a voltage divider, right? Did I do that right? R over 9. Probably not. What? R over plus R over 10R. I did it right. Wow, that's amazing. So you can repeatedly get an attenuation. You can get, V out to be 10% of Vn, but you cannot get V out to be 10 times Vn. You just can't do that with unless you have an active gain element, and that comes in the form of transistors. So, okay, let's say, we said you have this gain stage. We introduced this concept of this gain stage in the previous lecture, right? You have your bipolar transistor, you put a load resistor here, and you have a supply VCE here, you have a VN, and then you have a V out. So we said you can get gain from this. In fact, we showed how you can get gain, and we showed how the V out is VCE minus I sub C R sub L, and I sub C is I sub S exponential of VBE or VN really. So let me actually write this, sorry. So I sub C is, I sub C is I sub S exponential of VB, well, Vn. So I put that here, I sub S exponential of Vn over Vt minus 1 times R sub L. Okay, so basically, I guess the way I look at this is, to figure out the gain here, you get V out over Vn, and one way or another, you can kind of work out, you've got Vn on this side and V out on this side. Never mind what that exact gain will look like in terms of this equation, but you have gain, right? You have gain, you have a transistor there, and it's going to give you some gain, right? You get a small input voltage change, you get a large output voltage change. And I hope you guys saw that before. I'll give you guys some more examples today. So okay, so the question then is like, well, okay, why do I need an op amp then? Why do I need this thing with a gain of a jillion? I can just, however way this equation works out, I can tune this bad boy. I can pick R sub L. I can, pick I sub S or whatever it is, and I can get some, gain of 10x out of this. Okay, so the question is, can you get a repeatable, reproducible times 10 gain out of this? Question mark. So any thoughts about that? Any of you guys care to make a guess? Go out on a limb? No? Come on, guys. This is like, go ahead. Sorry, Jonathan.
Well, since you're saying that we have to use the op amp or whatever, I'm gonna guess no.
Good answer. I'm reading about this Socrates and the Socratic method, and there's always like somebody who like says, no Socrates. So true. So there's a rhetorical question. So you can tune it, right? Again, this is an example. If I set you guys off and said, hey, make this thing in the lab, make it have a gain of 10, you'll make it work. You'll just sit there and kind of tune it, pick up different resistors, etc. But here are the problems. Okay, now this I sub S, that is a big factor in this I sub C, that will vary a lot. If you guys remember, this has in production, you will not get the same if you buy transistor after transistor after transistors, none of their I sub S's are going to be exactly the same. They might vary by plus minus 25% or more, under the same conditions. They're just producing the stuff. There's variations in I sub S. They just can't control it too closely. Again, plus minus 25%, that will directly, with this kind of equation, that's going to translate directly to an error from part to part that you're making of plus minus 25%. So sometimes when you think you got a gain of 10, you'll get a gain of, I don't know, 7.5. Sometimes you'll get a gain of 12.5. Not good. I sub S changes with temperature. VBE, which is sitting, it's even worse. Sorry, VT. VT, which is sitting in the denominator on your exponential. We know, we keep saying this is 26 millivolts at room temperature. Well, but it's really, the equation of VT is KT over Q. So it's directly proportional to the temperature. So temperature goes up by 10 degrees. This is going to go up by quite a bit. And it's sitting in this denominator and this exponential. So it's going to really, really screw you up. Okay. And then VN, if it's VN is moving up and down by itself, let's say you got different microphones sitting here, and the actual absolute value of VN is changing. So sometimes the microphone might give you a VN of 0.8, like the way you designed it, but you get another microphone, plug it into it, you might get 0.82, or you might get 0.85, I don't know. And if you guys, I don't know if you remember, but we said a VN in a bipolar transistor changes by 60 millivolts. I sub C changes by a factor of 10x. So if from microphone to microphone, I only get 60 millivolts of, my starting point for VN, it'd be different. my I sub C changes by a factor of 10 times. That's like, so sometimes you get a gain of 10, sometimes you'd get a gain of 1, and sometimes you'd get a gain of 100. Imagine if you're trying to sell that product. No. So this, and then I mean, I'm not even going to talk about like as VCE changes, you know, lots of bad things can happen as VCE changes, etc. So I'm going to leave you with that concept. Not that this is not a usable circuit, but it's just, it works great as a building blocks for an operational amplifier. And I'll talk about that now. So just sort of leave with this thought that with this kind of circuit, you can get gain. And as we'll see, we can make the circuit as it is, you know, we can tweak it here and there. There's methods we'll use to just say add 1 resistor or a capacitor, or maybe add 3 resistors, something like that. Make this a lot more reproducible, but it's still not gonna cut it for most like 99% of actual production applications. But these are the problems with it. Again, you can tweak the hell out of this thing if you're just building one, and it's going to be sitting in a really controlled environment, same room temperature all the time. They're not going to take it out of the lab, and so on and so forth. And you're going to build one, and you're going to spend lots of hours on it. You can get it to do what you want, but that's not going to work, you know, as a product. It's something that you'll be expected to design as professional engineers. Okay, so now keep that concept. So I'm going to now go back to the op-amp and tell you guys a little bit about this concept of op-amp. And let's say we want to do the same thing, same example. Okay, so there's this concept. If you have this, this is the magic of op-amps. And again, you won't be tested on at the moment anyway. Maybe we'll start talking about this later on in the class. So sorry, this will be called out. There's this concept, very, 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 very important concept of negative feedback. And that does not mean that something bad's happened and you're hearing about it. It means that you can create, you can put this in put some stuff around this, okay, that by taking the output and putting it somehow back into the input in a way that this overall circuit, whatever I'm going to draw, is going to affect the input in a negative feedback way. It means it's going to dampen the changes on the input. This is a very hard concept to get your head around. So just, you can get very precise performance, okay? It doesn't mean you're attenuating stuff. It's a technique to use the output to make this overall, whatever we're gonna make, a stable, reproducible thing. It's called negative feedback. And typically, you want negative feedback in analog design. It's very, very, very commonly used. Very, very, very important to get precision. It's a signal processing technique. I'm not going to go into every aspect of it. I'll just derive it for this particular circuit that I'm going to talk about. So it sort of gives you guys an idea of what these op amps are and sort of what like negative feedback does, etc. So let's look at it. So let's say I'm going to somehow magically get a precise 10x gain out of this. What would I do? Well, I'm going to stick a resistor here and a resistor from this node to the output. And I'm going to call this R2, and I'm going to call this R1. And I'm going to make this V in, and I'm going to make this V out. And I'm going to hook this up to ground. Okay. Now, let's say I'm going to tell you guys a few things about this op amp. One thing is the current, whoops. So I'm going to call the current going into this negative node. I minus. So this is current going to negative input of op amp. And I plus is current going to positive input of op amp. I'm going to claim both of these are very small, so they're both equal to 0 approximately. Okay, why can I say that? Because I'm going to make the input of this op amp from bipolar transistors. And as we've seen, if you hook up the input, the base of a bipolar transistor somewhere, the current going into the base is going to be pretty small. Okay, so that's why it's important, as you'll see, why this is important, that there's very little current. There's always some current flowing into here and here, but that, let's say we can ignore it for a time being. And then let's say the gain of this op amp, like I said, this op amp takes the difference between these two nodes and amplifies it by this factor of A, and this amplification is very large. Let's call it, it's 1,000,000, just for sake of discussion, whatever. Let's say it's 1,000,000, but because it's made out of our bipolar transistors, we have a bunch of bipolar transistors. Let's say it changes from 1,000,000 to 10 million in production, right? Sometimes you get a part that's gain of 1,000,000. Sometimes you get one that's 10 million. Sometimes you get a 2 million, 3 million, whatever. Everyone is like crazy different, but they are all a very large value. Everyone is a very large value. Okay, so let's look at what the circuit does. Okay, so let's call this one I1. Let's call this current I2. Okay, so they're going to flow, they're flowing into this node. Okay, so this is Kirchhoff's current law going into this negative input node. So we're saying this current into the op amp is very small. So I1 basically plus I2 has to equal to 0. So this is Kirchhoff's current law. So I1 plus I2 equal to 0, or I1 is equal to minus I2. And then let's look at what I1 is. Well, I1 is going to be V in minus the voltage at the negative node of the op amp over R1. And I2 is going to be V out minus the negative input of the op amp divided by R2. Everybody with me so far? Any questions? Hopefully it's like pretty straightforward so far. Okay, so now the definition of V out. Remember, I defined V out to be V plus of the op amp minus the negative input of the op amp times the gain. Times this gain. Okay, I hooked up V plus to 0. So V out is just going to be minus V minus times this, oops, times this gain. Or the minus V minus is going to be V out over A, negative V out over A. Okay, so I'm going to plug this guy back into here, and then equalize the two. Okay, so I'm going to do, so I1 is V in minus, it's minus minus, so it's plus V out over A over R1. I'm just plugging this thing into this thing, into this guy. And this is equal to, it's equal to minus V out minus V out over A. So again, I'm plugging this guy now into this guy, and then plugging it in here over R2. Oops. Sorry, guys. Okay, so now let me move stuff around here. So I get V in over R1 is equal to minus V out over R2 minus V out over A R2. I'll just do V out over R. Let me do it this way. V out over. Everybody with me? I'm just moving stuff around here. Okay, so I got V in over R1, V out over R2, V out over R2 over A, V out over R1 over A. So now this is the magic of having high gain. So now I said the gain is high, but it can be 1 million or 10 million or whatever. Now notice, as long as this gain is high, and I mean very high, right? 1 million, 500,000, whatever, I can say this is 0. This is very small, right? I got whatever voltage I got on my V out. I'm dividing it by this really large number. It's 1 million. It's basically like kind of infinite. So it makes this term go to 0, and it makes this term go to 0. It doesn't matter what R2 is. R2 could be 1,000 times bigger than R1, or vice versa, or V out could be anything, whatever. As long as this gain is very large, these terms will go essentially to 0. There'll be some amount of error, but it's be it'd be like much lower than a percentage. Very low. Okay, very low. So, and it doesn't matter the exact value of the gain. A gain could be, again, it could be off by a factor of 10, could be off by a factor of 100. As long as it's a big number, it'll make these guys go to 0. And then what will I be left with? I'll be left with V in over R1 is equal to minus V out over, R2. And so my overall gain is V out is equal to R2 over R1 V in. And I can make R2 equal to 10x R1. Okay, and I got my gain of 10. Okay, so now let's see, why is this reproducible? Well, okay, so it's pretty cheap and easy to buy resistors with 1% matching. Okay, you can buy, at 10K ohm resistors that are plus minus 1%, and 1K ohm resistors that are plus minus 1% all day long. You can just, so, they might vary a little bit, but 1% is pretty good. You'll have a gain of 10 or a gain of 10.01, or a gain of 10 or a gain of 9.99. Very precise, right? The other thing is, these two resistors that you're buying are made from, you could buy them to be made from the same material. That means if the temperature goes up and the resistance goes up of one, well, the resistance of the other one's going to go up by the same percentage. So the gain is going to track with temperature, because you are basically, you're using the same external component, or external component made from the same material that has the same temperature coefficient. Okay, so it means that they're both going to go up, they're both going to come down. Now, again, assume with temperature, as temperature changes, the gain of your op amp goes from 1 million to 900,000 or 700,000, or goes from 1 million to 2 million. It doesn't matter. It's just, it's just this error, because you're just, either way, you're sending these guys to be approximately zero, or very, very close to zero compared to these values. So it doesn't matter. Like, the temperature, the op amp is going to move around a lot with gain. In production, it's going to change. In the temperature, it's going to change. If the power supply in your op amp changes, it'll change the gain. But it doesn't matter as long as it stays to a high value. Okay, so now by using this component and these external components that you can match in a negative feedback configuration, I can get a very precise, very repeatable voltage gain. And again, thanks to our decades of people screwing around with these op amps, there are op amp circuits that do, I don't know how many different, I really have no idea how many different types of op amp circuits there are, but many, many, many. So they do many, many different functions. They get precise addition, precise subtraction, precise division, precise, you name it, integration, all sorts of stuff. Okay, so you have this thing. So now coming back to this circuit, or the circuits we're studying in this class, somehow you need to create this very high gain in this op amp somehow. Okay, but like, how do you do it? Well, the stuff in this op amp is made out of these circuit blocks that we're studying in this class. So it's probably usually it's not practical to use these circuit blocks as it is, although sometimes I'm asking for examples or suggesting examples, trying to make it sound like you will be using it, like in a microphone or whatever. But practically speaking, you cannot use these, but you use these to build the op amp. Okay, so I've got an example. Let me see if I can bring it up. I put it in the announcement. It's kind of a cool page. You see some of these, but I thought it would be kind of interesting for you guys. Let's see, where am I? Want to share. Here we go. Okay, so hopefully you guys you're seeing something that says Ken Sheriff's blog. So this is, this talks about this op amp that's, very old, but, I used to use it, still can buy it. I'm sure it's like just some component that you can buy. This can is something that is like a typical package. This is like the size of maybe it's like 5 millimeters across, something like that is what it looks like. And it's got a bunch of pins that go into your printed circuit board or your wire wrap board, etc. If you cut out the top of this can, and this is what the guy did. If you look at what's inside, it looks like this is the chip. This is a silicon chip that's in there, that's got the op amp in it. And so this is sort of a zoomed picture of the chip. And this is a very old chip when you could, the size of the components, these are huge transistors. So imagine a chip now. So, maybe this chip here is a millimeter on a side, I don't know. But so a chip right now could, would, no exaggeration, has, 10 million times, 100 million times more components per unit area than this chip. But this is kind of nice because you can still kind of make out what things are. And like the components are made out of these bipolar transistors that we're looking at. So for example, NPN transistors, and they actually, we're not going to talk about how you build those specifically. We look at them in this kind of a block level thing. They give an example in this website, just kind of neat, but again, it's more than you guys probably need to do in this class, and different circuit structures, etc. But what I wanted to show you was, do you guys all see this schematic? I hope you see the schematic with a bunch of bipolar transistors. And so that's what the op amp is made out of. It's made out of a bunch of the circuits of simpler bipolar transistors that together give you a very high gain and a bunch of other performance parameters, but primarily the sort of the active ingredient in op amp design is a very large gain. So what you can do is you can put in a bunch of like gain circuits in basically in series, and let's say each one of the gain circuits has a gain of, for the sake of discussion, has a gain of I don't know what's a good number. Let's say each one of them has a gain of 100, right? So if you put 3 of them in series, I don't know if it's going to be 3 or 4, let's say 3 of them in series, you're going to get a total gain of 100,000. And let's say now each one of those blocks has a gain of 100, give or take, I don't know, 10%, 25%. Overall, when you multiply their gains together, you still get a big number. You know, it might be 50,000, it might be 100,000, it might be 200,000. But all you have to do is to make sure it's a big number. But each one of these block layers, again, it looks very complicated, but they are versions of the things we're looking at in this class. So, you know, there's sort of stuff. It's kind of an interesting paper either way, but, you know, you can kind of see one of the things, couple of things, you kind of click on these and see which transistor it actually is, kind of amusing. But, you know, one of the things that's, for example, is important to us right now is notice these inputs are going input, whatever it is, minus input and plus input for this op amp are going to these bases of these bipolar transistors. And if you remember, we assumed that the current going into these should be very small. And that's why it's important that the base current is very, very small. Okay. So anyway, this is just something for you guys. Lots of, you know, it's a loving website dedicated to this really old op amp, which a lot of us old people have used. They got different, better things, different things now. Close that, stop sharing. Let me go back to this and what was the other point I wanted to make? Boy, I had one last point I wanted to make for you guys about these op amps and things. Shoot. So another concept which I think is cool here is a concept we'll talk about. We talked about a little bit in diodes, etc. Notice that what this feedback structure does, so this is sort of what's called feed forward, this is called a feedback, together with the gain and all this kind of other stuff, they make sure that the voltage change in this node is very, very small. So if you get a change in voltage here, you get, you know, a 10x change here because of this feedback, but this minus node is always going to be more or less around ground. If this thing, it's going to be, if this is hooked up to ground, so more or less end up, this feedback structure, no matter what this input does, this feedback makes sure that this guy comes back to the same value. Just how it works. Again, you got to get some experience with feedback to get that. But the nice thing about this thing is that, as we'll see, a lot of what we're going to use to assume is the concept of small signal models. and this important thing about small signal analysis, we saw it in the diode, if you guys remember, etc. We're assuming that the voltage changes are very, very small. That's how we can use these small signal models to make our designs easier. But as you can see, if you put your circuits in this feedback loop, basically the feedback is going to make sure that the changes in voltage that are actually seen by your active devices are going to be very, very small. So this is just like a really this negative feedback concept with just negative feedback with gain circuits is like such a powerful concept because it does a whole lot of things that you want to do. It's really, really a powerful concept, and that's why it's so prevalent. Okay, guys, so that was a, kind of a long-winded excursion compared to what we're doing. But again, what I'm really in fear of is that you guys are gonna go through this class and a lot of these key concepts, like you won't know why you're studying these things or where things are going or, how the stuff's gonna be useful or whether it's useful or not. So I wanted to just kind of like give you guys that overall view about what we're doing. Okay, so what we're doing is, again, the baby steps of building these usable circuit structures, and by usable in engineering, in electrical engineering, we're talking about stuff that is robust, is producible, and therefore, you won't get, the upshot is you won't lose your shirt selling these things. It won't cost a lot so that your profit margins don't suffer, and you won't get a whole lot of returns because people buy them and go, well, I can't use this. This isn't what you promised to sell me because this display is too dark or it's too bright or whatever. And here's a return, right? So that's our goal. Okay, so that was a long excursion. Now let's go back to, I think, where we were, which is our bipolar amplifier, okay, or which is like the basic building block of these circuits. So let's see, where was I? I wanted to give you guys. Okay, so now let's get back to our bipolar transistor again. So, we have this, let me give you guys now like so after all that's said and done, the upshot is like these kind of circuits that we're looking at is just a component of a bigger circuit to make it usable. But we still have to study these in detail to make sure that we know how to implement them in these bigger circuits. So back to using this guy as a gain example, let's look at our circuit again. So we have this guy that goes to, we have a load resistor. It goes to okay, so I'm going to use from now on, I was using, so a couple of things that people can go wrong here, right? So I was using something like this, and we call this VCE, and we got this being VBE. Okay, so you have to be really careful with these concepts. Okay, so VCE is the voltage from the collector to the emitter. So notice now I have a resistor between the voltage node and the collector. So this voltage is no longer VCE. So if you use this voltage to figure out, if you're in forward active mode or not, it's not going to work. This is the voltage at the collector, and this is the voltage at the emitter. So the difference between these two voltages is VCE, not this voltage. So this voltage is the power supply, and by convention, the power supply in bipolar circuits is almost always called, positive power supply is always called VCC. Don't ask me why. So I'm going to call that VCC is 10 volts. Okay, the other thing that you have to be careful about is VBE. VBE is the base emitter voltage. So if I put a voltage source here, okay, I can call this VBE. I can call it something else too, but this, whatever this is, it's going to give me my VBE, right? The base emitter voltage. But for the sake of discussion, as you'll see in a few lectures, let's say I put something here. I put a resistor here. The VBE is the voltage between the base and the emitter. It'll no longer be, so if this is, like, say, 0.8 volts, so I'm going to call it VN. So my VBE in this case is no longer 0.8 volts, right? It's the voltage from this point to ground is 0.8 volts, but my VBE is from the base to the emitter. I don't know. We'll see how you can figure it out. But right now, I don't know what what voltage drop happened across this resistor to see what voltage my emitter is at. Okay, so I have to use the base emitter voltage and not just whatever's hooked up to my input isn't VBE. You got to be careful about that. And whatever is hooked up on this top is not VCE. This is the collector, this is the emitter, that's your VCE. This is the base, this is the emitter, that's your VBE. So you got to be careful about that. So I just wanted to mention that because it's a good way to get in trouble later. So let's say we have this situation, and let's say I put a battery here that has a voltage of, so V battery, and it's got a voltage of 0.8 volts. Then I'm putting a voltage source here that's got a voltage, so it's going to have a voltage jump on this. So I'm going to have a voltage source on top of a battery. That means, for example, if delta V is plus 100 millivolts, the voltage at this node, so V in is equal to 0.8 volts plus 100 millivolts. So it's going to be equal to 0.81 volts. Okay, so so let's see what happens when for different values, okay, of what happens here. Now let's say for the example, so I'm going to set my RL to be 100 ohms. And so what's the first thing I can do? So in terms of seeing what happens when VBE is at a certain value, okay? So, or let's just think of it as a general case. So if, assuming this is in the forward, this transistor Q1, I'm going to call it Q1, is in the forward active mode. If I look at what this circuit translates to, is I'm going to have a current source. So I can replace this Q1. So Q1, I can pretend it's a current source with a current I sub C. Okay, then I have a resistor R sub L, which is equal to 100. And I have this VCC of 10 volts. And I'm going to take my V out from the collector of this transistor, which I'm just representing at a current source. As far as this side of the circuit's concerned, this guy just looks like a current source with some value which is dependent on the input, but it just looks like a current source. Okay, with I sub C equal to I sub S exponential of V bat plus delta V over VT. So basically the voltage at V out, this is another place people get confused about, is VCC minus the voltage at or across R sub L is equal to V out. Why is that? Well, so V out, when I show a node, a single node for the voltage, remember that a voltage is the difference in potential energy between two nodes. You can, it doesn't make sense really to say the voltage at some node is a certain volt, sorry, the voltage at some node is a certain voltage. The only way that makes sense, of course, we say it all the time, is because the implicit assumption of that is you're talking about the difference between that node's voltage and ground. So you're always talking about the difference between two nodes as being a voltage. Just one node by itself, as there's no definition of that thing having a specific voltage. So if you wanted to, in the lab, if you were gonna check what V out is, you know, let's say you have a multimeter. I don't know if you guys have used multimeters or oscilloscope. You have something you need to plug into V out, but then you have another connection on that multimeter or you know, scope probe or whatever, which you got to hook up to someplace that you're comparing V out to. And again, when we don't say anything, you're comparing it to ground. So if you had a multimeter, you'd connect one end to V out and one end to ground. Okay, so if you look at KVL, you end up, your loop goes from ground to VCC across the R sub L and then to V out back to ground. And remember that these two grounds, or all the grounds, are connected. So this is a KVL loop here, and that has to equal to 0. So KVL would say that V out, well, let me just start with the actual VCC. So VCC, so sorry, let me do it this way. So first step is 0 plus VCC, which is this node. So I have ground plus VCC minus the voltage across this RL, VRL, minus V out is equal to 0. So you end up with, let's say our VCC is our VCC is 10 volts. The voltage across RL is IC R sub L, with, you know, IC given as this as a function of our input. So basically we say that if I move this around, we end up with V out is 10 volts minus IC times RL. Now let's, okay, so this is our, what it looks like, right? So let's just to look at a few examples. Let's say I sub S is, for this transistor, is 1 times 10 to the minus 16 amps. And V sub T is, you know, KT over Q. And let's say we are at room temperature. And so this is approximately 26 millivolts. Okay, so let's take the case 1. Let's say you have, this is time. This is voltage. Let's say, at some time, so this is t equal to t0. At some time t equal to t1, delta V goes from, so if I plot just the input of the Vn, it's always at least V bat, right? It's this is a battery, so it's always 0.8 volts at least. And then let's see, delta V goes from 0 to 100 millivolts at time equal to T1. So it's going to look like this. Vn is going to look like that. It should be flat. So this delta is going to be 100 millivolts. So now let's see what happens on the output. So at time t equal to t0, I sub c is I sub s exponential of 0.8 volts plus 0 volts. Okay, so it's really just 0.8 volts. I put this so that I'm consistent with my general equation for I sub c over 26 millivolts. And if I plug in my I sub s and V sub t, this ends up being equal to 2.3 milliamps. And then at time t equal to t1, I sub c is equal to I sub s exponential of 0.8 volts plus 100 millivolts over 26 millivolts. Oop, I screwed up, guys. Sorry. I wanted to make this 60 millivolts. Sorry. To make my math a little easier. Okay, so plus the reason I wanted to make it 60 millivolts because I know I sub c is going to go up by a factor of 10x every 60 millivolts. So if this is 2.3 milliamps, that means I sub c is going to be 23 milliamps. If the at t equal to t1, t is greater than t1, it's going to equal to 23 milliamps. Okay, so what was going to happen here? So for V out, so V out at this point is going to be 10 volts minus ICRL. So 10 volts minus 2.3 milliamps times 100. So it's going to equal to 9.77 volts. So my V out's going to be, up here, way up here. Let me actually draw this so that I can give it some semblance of, oops. Oops, didn't want to do that. So if I was gonna, that's still probably not drawing to scale, but if I was gonna draw it, the V out would be up here somewhere. So at this point, it's gonna be 9.77 volts up here. And when I go to t equal to t1, V out is going to be 10 volts minus 23 milliamps times R sub L, or 10 volts minus, I think it's 2.3 volts, so it's equal to 7.7 volts. So the output's gonna go like that. So that's what our, so this delta V out. So the reason I decided to give you guys this example is because it kind of like helps me to think about the time change of circuits. And this is showing us a few different things. Okay, so one is that the gain of this circuit, if I define it as, whoops. The gain, if I change it, define it as the change in output voltage over the change in input voltage is, in this case, 2.807 volts over 60 millivolts, or what does that give me? Which is minus that. It's 34x gain. Okay, so why the minus? It's because when the input goes from low to high, the output goes from high to low. So it's got this sort of negative polarity input to out input. So sorry, I keep forgetting this minus. Okay, but it's okay because, you know, I'll know what to do with it. I know about it. This is very common, but basically a small change, a very small change on the input gives me a larger change on the output. By, in this case, by a factor of 34 times bigger. The polarity is different. And notice that the offsets are also different. You know, this input is sitting here and the output is sitting here. And that's because we haven't done anything to give them the same offset, right? So this one, this output is being defined by this voltage drop across R sub L. And this is an input from ground to something higher, or from VB to higher. So it has these, you know, interesting features to think about. Okay. So anyway, I can go through and show that, you know, as I make the voltage increase higher, let's say if I wanted to get 4 times higher gain, for example. Well, maybe won't get to that example. But anyway, sort of, I wanted to give you guys an example of what this actually looks like when we're talking about gain as a change in output with respect to input. You know, how it would look. So, you know, if I had a 1 millivolt change here, so if I just had a small 1 millivolt, I would get a, you know, 34 millivolt drop here. Okay, because I would still have a 34x gain. Okay, it hasn't changed very much. So I'll stop right there, guys. Any questions? No. Okay, guys. Well, I'll let you go. I'll talk to you guys. Oh, yeah. So I'll talk to you guys on Thursday.
Thank you, Professor.
Professor.
Bye.